Okay, here we go. All right, welcome to Physics X, Extraordinary Concepts in Physics. This 15-minute or less snippet will be the first of the double-slit experiment lectures. So we got a whole bunch of these. So first I'll say, wow, it's really cool stuff. The double-slit experiment is strange stuff. So let's review this. Physics X, also called Extraordinary Concepts in Physics, as it says here. Anyone can be here, can view these lectures, although it's aimed at upper-level physics majors. One of the reasons for this kind of course is because a lot of the stuff that physics majors take deal with the formal mathematical stuff, and they tend not to delve into the conceptual stuff. So the idea here is to stay away from the mathematics and go right for the heart of the concepts. No textbook because Wikipedia is strong in this area, so I show you the Wikipedia links. If you're just following this on the web or through iTunes or something like that, you can just go to Starship Asterisk, go to the front of Starship Asterisk, click on Physics X, or you can just go to this link, which I know looks small, but if you're really interested, you could probably find that. All right. Let's talk about quantum mechanics in general. One of the heroes of me in this course, frequently cited in this course, is Richard Feynman, who has said, I think I can safely say that nobody understands quantum mechanics. So don't feel bad. Oh, I don't understand that. There's something wrong. I need to take off a month, or I'm not a good physics major, or I'm not an intelligent person because I don't fully understand quantum mechanics. So nobody does. So I don't. So Richard Feynman doesn't. Nobody fully understands it. It's really strange stuff. So we're struggling to understand it. There are new experiments going on where people disagree on what the results of those experiments would be. So there's another quote I'll give for Feynman later, but here's another one. Any other situation in quantum mechanics, it turns out, can always be explained by saying, you remember the case of the experiment with two holes, which is the double-slit experiment? It's the same thing. So the double-slit experiment is one of the most fundamental experiments in physics and quantum mechanics. So we're going to look at it in the next several lectures. So 1, 2, 3, 4, maybe 6 or so 15-minute snippets, maybe a little bit more, just trying to get into the different takes on the double-slit experiment, change something slightly different in the double-slit experiment. So if you want to understand something, change it slightly and see how it affects things. So I'm going to do that a lot with the double-slit experiment. Let's change a little. What happens now? Change something else. What happens? Well, we're going to find out a bunch of them. We can't do it all, and we're not going to fully understand, but maybe we'll understand a little bit better. Okay, so the double-slit experiment, sometimes called the two-slit experiment, it illuminates the uncertainty principle. Interference, entanglement. These are all things. There'll be a whole lecture down the line on entanglement. Coherence and decoherence. And how truly strange our universe in quantum mechanics is. All right, so what is the double-slit experiment? So let's get this clear. So there's a source here. Many times there's like a light bulb here, or something, or a laser. And it shines through something. You can just have the laser. You don't really need, but it's sometimes simple to say, well, there's a single slit screen here that it goes through. And it gives a wave that goes out, and these waves then hits two slits. So this could be a source, this could be two slits, and these two slits then, the light from these two slits, sometimes electrons, go out, and these two slits seem to interact. The light coming through those two slits seem to interact. And they hit a screen, an image screen right here. And this image screen has different patterns on it. And if it was easy to predict the patterns, we wouldn't be here. Sometimes the pattern is very strange. So it gets right to the heart of quantum mechanics many times to understand what pattern is going to appear on that screen. So we'll step you through it. Still, when I change something, I'd like to agree on what the basics are for the usual two-slit experiment. So the source is a point source that illuminates both slits equally. Therefore, one slit isn't necessarily brighter than the other, unless I say it is. And then that might be the thing that we change. Therefore, both slits, we usually see this mean number of photons, the same number of photons going through. Both slits are considered to be identical. They have the same width. They have the same structure around them. If there's some kind of material around them, don't worry. Unless I tell you there's something different about one of the slits, and I will sometimes, they'll be the same. The width of the slit is usually referred to by the parameter d, although I'm going to try to lay away from the mathematics. The wavelength of the light The wavelength of the photons is going to be considered to be lambda, a Greek character, which is usually used for wavelength. Now, a lot of people use frequency, they use energy. Yeah, that all works, but I like to stick with one variable, which is lambda, which is the wavelength of the light. Wavelength of what? Is this the difference between peaks in the electric field, the magnetic field? Well, that's a very Maxwellian view of photons. Still, one might consider it to be something like that. Is it the peak-to-peak of some kind of probability wave? Maybe. It is a characteristic length scale for which photons seem to respond. Now, the slit screen, so usually you will have a source here. Then you will have the slit screen here, and then you have the image screen there. So the slit screen will be considered in this part and this part completely opaque, unless I say otherwise. So you don't have to worry about photons tunneling through or some percentage transmitting through. It's just going to be, they can't make it through, okay? Photons don't go through there. Here, though, it's going to be considered, unless I say otherwise, completely transparent. So once you have an opening, a slit, or two slits, as the case may be, there's nothing there. Don't worry about air molecules. Don't worry about maybe a window pane. Unless I say to worry about it, assume there's nothing there and it goes right through. All right. Usually I will consider that photons will all have the same wavelength lambda. Also, the image screen will be able to record things usually with arbitrarily high accuracy. So here's the double slit screen, here's the source. So once things hit the image screen, this is the slit screen, it hits here. It could be, think of it, it might be a digital camera or something. And digital cameras have pixels of known sizes, but think of it as like a digital camera with very, very small pixels. So you're not worried about the size. All right. So usually, for this to work well, although we'll be moving things around, the width of the slits, oh, I might be changing from earlier variable, I have to go over it, is W, and W is going to be a few lambda. So W is going to be greater than lambda, usually. The distance between the slits is also going to be a few times lambda and also a few times the width of the slits. Exactly how much doesn't really matter for the qualitatively, conceptually what happens. If you wanted to calculate exactly what happens, then you'd need to know. We're going after concepts here. All right, so a double slit experiment here has here's what happens with a single slit experiment here. Now with a double slit experiment, you're going to get similar patterns, except you're going to get these dark spots there. That's the interference. So it looks actually similar to a single slit, a little bit wider because you have two single slits, but the interference is the key part that we're looking for usually. So if photons traverse the two slits, they might interfere. They might not. Interference pattern is created at the image screen. Geometric progression of each slit on the image screen shows no overlap region. Oh, so that's interesting. Okay, so here you have, if you had a source that was infinitely far away in this direction, then you would just get the geometric progression of each slit onto the screen, which would be a spot here and a spot there. They wouldn't overlap. If they don't overlap, you can't have interference. So this is what's wrong with many of the videos that appear on YouTube about the two-slit experiment. The first one shows them not overlapping, and the second one shows them interfering. How does that work? They have to overlap to interfere. Let's see, at any point the image screen, the projection of one slit is usually brighter than the other because one's closer. Interference pattern are not, the minimum are not usually zero, even though many times they're thought to be, or not thought to be, considered to be. We were examining wave-particle duality. I'm going to speed up a little bit. So here's some questions here. So this is what I like to focus on. I like to make people think. I like to focus on experiments because that's the root of physics, and I like to focus on experiments that get to the root concepts if I can. So the usual double slit experiment, as I described, is done, except now the photon rate is reduced so that, on the average, only one photon passes the slit screen at a time, just one at a time. And now another photon, and now another photon. What happens? Is there no interference pattern that appears because you only have one photon? Do you have a normal interference pattern eventually appear after lots of photons eventually go by? Does the image screen remain blank? Or does the experimenter lose interest and begin to watch television? Which of these do you think would happen? So please pause the video. I got to keep going if I'm going to get through these. This is one of the strangest things in physics. A normal two-slit interference pattern will appear even though only one photon at a time is going through. You can do this with electrons, photons, one at a time. And that's because, to paraphrase a famous thing from Dirac, and we'll get into this a little bit more, photons interfere only with themselves. So if you're looking for the two slits to interfere by two different photons interfering, that's less frequent and less coherent, as we'll see, than photons actually interfering with themselves. So you can consider that the photon goes through both slits. It's a little bit like the cat being dead and alive. This assumes that nobody around ever, anybody, will know which slit any individual photon went through. Okay, so let's replace this with electrons. Well, I sort of gave away the answer. The unusual double-slit experiment is done, except now electrons replace photons. So is this peculiar to photons? Can this work with things that have mass? With these replace photons with electrons, do you get an interference pattern? Do you get no interference pattern? Does the screen remain blank because electrons don't work? Or do monsters from the deep devour Cleveland? So you can pause this and think about that. Do electrons make the double-slit experiment any different? Do we need light? Does light have such long wavelengths that it causes this to happen? Or not? Think. Pause if you must. Here we go. Boom. A normal interference pattern appears. You don't need just photons. This works with anything, practically. Any particle the Compton wavelength then replaces lambda instead of the photon wavelength. This again assumes that nobody knows which slit the individual electrons went through. Okay, so now the usual double-slit experiment is done, except now one slit is blocked. Now we're going to have a whole bunch more of these next lecture, and they're going to get stranger and stranger. So this is one of the easy ones. So if you block one of the slits, do you still get some kind of interference pattern, or would this negate the interference pattern? So you can vote 1, 2, 3, or 4. Janitor could offer to unblock the slit. Would that help? So this is probably one of the easier ones. Next time they're going to get so hard you might not be able to decide. If you're proud of yourself for getting all of these, I know. I'm the person. Feynman said no one understood quantum mechanics, but I got all of these right, so I must understand quantum mechanics. Tune in next time, and the next time after that. The answer to this one is, as you might have guessed, no interference patterns appears. If you block one of the slits, the photons go through that slit, and you get a single slit pattern. You can get diffraction, but you don't get interference between the two slits. And with that, I will bid you adieu until next time, when we have many more very strange two-slit experiments, and even more past next time. There's going to be a whole bunch of these. We're going to really go into this in detail. See you next time. As it says here, anyone can view these lectures, although it's aimed at upper-level physics majors. One of the reasons for this kind of course is because a lot of the stuff that physics majors take deal with the formal mathematical stuff, and they tend not to delve into the conceptual stuff. So the idea here is to stay away from the mathematics and go right for the heart of the concepts. No textbook, because Wikipedia is strong in this area, so I show you the Wikipedia links. If you're just following this on the web or through iTunes or something like that, you can just go to Starship Asterisk, go to the front of Starship Asterisk, click on Physics X, or you can just go to this link, which I know looks small, but if you're really interested, you could probably find that. All right. Okay, here we go. All right, welcome to, let's talk about quantum mechanics in general. One of the heroes of me in this course, frequently cited in this course, is Richard Feynman, who has said, I think I can safely say that nobody understands quantum mechanics. So don't feel bad. Oh, I don't understand that. There's something wrong. I need to take off a month, or I'm not a good physics major, or I'm not an intelligent person because I don't fully understand quantum mechanics. Physics X, Extraordinary Concepts in Physics, this 15-minute or less snippet will be the first of the double-slit experiment lectures. So we got a whole bunch of these. So first I'll say, wow, it's really cool stuff. The double-slit experiment is strange stuff. So let's review this. Physics X, also called Extraordinary Concepts in Physics.